Okay, so I want the energy of my photon. Oh, that's interesting. Everything I just wrote, my program crashed, but we had just determined that the energy per atom was 7.56 times 10 to the minus 19 joules per atom. So the ionization of one atom would be 7.56 times 10 to the minus 19 joules. So we want the energy of our photon, which is equal to hc over lambda, to relate to the wavelength. I want that to be greater than or equal to 7.56 times 10 to the minus 19 joules. So I can multiply lambda over to here, and I can divide both sides by 7.56 times 10 to the minus 19. So that shows me I want my wavelength to be less than or equal to. Do you see how I get the wavelength on the side, on the less than side, by when I multiply both sides by lambda? So that shows that lambda, we want it to be some value or less than hc divided by 7.56 times 10 to the minus 19 joules. H and C are on your sample info, so if you need to double check those, that's fine. I'll just say them here instead of writing them out, but it's 6.626 times 10 to the minus 34 joules times seconds times 2.998 times 10 to the 8, and then divide by that energy. And I get 2.63. Get that my wavelength needs to be less than or equal to 2.63 times 10 to the minus 7. And the unit comes from joules times seconds times meters per second for the speed of light. So there go the seconds, and then the joules cancel. So I get the unit out here in units of meters. And then I convert to nanometers. 1 nanometer is 10 to the 9 nanometers. So multiply by 10 to the 9. And I get 263. So I want wavelength less than 263 nanometers to cause electrons to be ejected by this particular metal. So if you have a question about the photoelectric effect, you have to think one photon versus one atom. If you're given the ionization in kJs per mole, we simply convert that to the ionization for one single atom, and then calculate the wavelength associated with that transition. Then another detail is that I may have been able to get to this answer just by thinking about the choices. Wavelengths always need to be some value or lower to be some energy or greater. So usually in these questions, if we're looking for a wavelength, it has to be some value or less, not some value or more. If we go to a higher wavelength than 263, that's too low of an energy to cause the ionization of the metal. That would contain an energy less than 7.56 times 10 to the minus 19 joules. We need an energy of that value or greater so that the photon, each one photon, has enough energy to break that electron's attraction to the nucleus. Okay, let's move into question 3. So in order for an electron to transition from n equals 1 to 3 within an H atom, what has to occur? It's just simply the absorption of energy somehow. So we have to have the atom in n equals 1, the lowest energy level. The jump to n equals 2 is a pretty big jump in energy. The jump to n equals 3 is not as high, not as big of a change. So this delta here of energy is greater than this change in energy. And then that's greater than the 3 to 4, which is greater than the 4 to 5. So as we're going up in energy levels, they're coalescing together to a lower energy. But to go from a low end to a high end, we have to have the absorption of energy. So the atom has to absorb energy. It could absorb it through absorbing a photon. That's probably the most likely way. Absorbing high voltage energy through absorbing energy by some means. And then if we're coming back downward, so for a photon returning back down, then that's the emission of energy. That could give off a photon of light is the most likely way that an atom undergoes this transition. It gives off a photon of light equal to the change of energy the atom undergoes. So we emit energy downward, absorb energy upward. And then we don't emit photons upward. We could absorb photons upward. And then we're not losing electrons in this process. We're simply moving the electrons from spinning around this region to a slightly larger average radius spinning around the atom. So you just think we're going from a smaller orbital to a bigger orbital from n1 to 3, and then backwards. And then one last thing to point out, since this question actually says n1 to 3, you can absorb from n1 to 2, or from 2 to 3, or directly from, in this case, n1 to n3, or you could return from n1 back to n3. that should be a high. The 1 to 3 is a big difference of energy. We would expect that to be in the UV region because it has a great energy. We know the 3 to 2, 4 to 2, 5 to 2, 6 to 2 are the emissions in the visible region. So those are relatively low energy compared to the UV transitions from arising to and from the 1 level. And then the values arising to and from the 3 level are associated with being in the infrared, the lower energy region. So which transition below for number 4, for an electron in an H atom, could emit a photon of the greatest wavelength? So the greatest wavelength photon would correspond to the photon, of course, of lowest energy. So if we go to a greater wavelength, that's a lower difference of energy. And then if we're going to undergo emission, it has to be from high N to low N to have an emission event take place. Unfortunately, all my choices are high to low N, so I can't rule out any of the answers based on some of the choices requiring an absorption of energy or the absorption of a photon. So all the transitions in A to D would give off a photon if they were to take place. But the issue here is that from my 2 to 3, big difference of energy, 3 to 4, smaller, 4 to 5, smaller, 5 to 6, even smaller. So the relative order of the energies goes something like this. So the 6 to 5 would be a really small difference of energy, and that should correspond to having the greatest wavelength. We should have a slightly shorter wavelength because a greater difference between 4 to 5 of energy, even greater for the 4 to 3, and then finally into the visible higher energy for the 3 to 2. So all of these we'd expect to be in that IR region, and then this to be the shortest wavelength for that smallest difference of energy. So a question like 4 is just getting at, do we understand the relative difference of energy as we go up in N? Is that, think of the electron moving from this orbital to this orbital, big jump in energy, to a slightly bigger orbital, smaller difference of energy, even slightly larger orbital, even less of a big change in energy. So as we go up in N value, the next successive amount of energy increase is becoming smaller. The conclusions derived from which theories applied to an electron supports the use of probability distributions or orbitals for where electrons are in multi-electron atoms. So which experiments or conclusions is that we are making that lead us to probability distribution diagrams, i.e. orbitals for atoms? And it was the Pauli exclusion principle along with the de Broglie wavelength. So it was the idea that matter could behave as a wave, that was the Broglie wavelength, and then as a wave that we did not know precisely where it was in any given moment when we compare the uncertainty in velocity to the uncertainty in position. This led to, we don't know an electron as a discrete particle, it's more like a probability distribution. So electrons can behave as a wave, and a wave that we don't exactly know where it is, so we treat it as a probability distribution. So that was the result of de Broglie and the uncertainty principle. The other, like Bohr model and Balmer series, were getting at the transitions of the H atom, important experiments, but it had nothing really to do with the actual discovery and invoking of orbitals and probability distributions. In fact, Bohr didn't know anything about orbitals at all, and you could say even Bohr, in some ways, perhaps violated the Pauli exclusion, or not the Pauli exclusion, Bohr violated the Heisenberg uncertainty principle because he made it seem as if the electron radius was simply changing as if it were a constant as you go from N1 to 2 to 3 to 4. The average radius of the electron may be changing, but the specific radius we don't ever know, or we can't know within the limitations of the uncertainty principle. Okay, so number 6, what about quantum numbers and their range of values, and what can we say about an orbital with an n of 3 and an m sub l of -2? And so when n is 3, we know that L can be equal to 0, 1, or 2, but not 3, because the highest L can be is n minus 1. And so this would refer to the 3s, the 1 would refer to the 3p, the 2 would be the 3d subshell. But the range of m sub l's, the m sub l range would just be 0 for the L0, it'd be -1, 0, +1 when L is equal to 1. So I can't have an m sub L of -2 with the L value of 0 or 1. I can only have it within this particular subshell when I have an L of 2. So I can range from -2, -1, 0, +1, +2. So I get the range of 5 orbitals within the 3D subshell. So the only time I can have an m sub L of -2 would be for this particular n value when L is equal to 2. Because if L is 0 or 1, even though for an n of 3 we can have an L of 0 or 1, but those particular combinations of L with that N cannot have an M sub L of minus 2. If we had a slightly different question, if we said same question but N equals 4, M sub L is equal to minus 2, which subshells could have that? Well, when we have an N of 4, the L could be equal to 3, and then M sub L of minus 2 is within the range of this L value's M sub L. So the M sub L here would be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So the range of M sub L are telling you that you have 1 S subshell, you have 3 P subshells, and then for the D's that you have the 5 D subshells, and then if you have an F orbital, you have 1, 2, 3, 4, 5, 6, 7 F orbitals within any F subshell. So the range of M sub L's are telling you the 1, 3, 5, 7 orbitals within each of those subshells. So within this subshell, the L could be 2 or 3 to have that particular M sub L. So for the given question, the only possible L value would be 2. For the L that could give us a combination of common numbers of N of L, M sub L minus 2. Moving on to the next page. Again, if you're coming in, this is the chapter 6 review number 2 packet from the daily quiz area. So considering the ground state of titanium, electrons occupying which subshell are on average furthest from the nucleus? This is a question I'm not sure we thought too much about, but it's one that's worth addressing here on this question. It'll help us in the chapter 7. I'm not even sure we would put a question like this on our test without having seen chapter 7. So this question will be important for us to think about as we proceed into chapter 7. So titanium, we know its configuration is this. We know it's the argon configuration. That's the nearest preceding noble gas to titanium. And then it's the 4s2. We're filling into the 4th row of the periodic table. And then it drops back to the 3D subshell. Our first D combination is N3L2, of course. And then we put 2 electrons, titanium is the second element, into the D block. And so for this configuration here, if we wanted to do a diagram, which we don't necessarily have to do for this question, we're picturing 4s2 and then 2 unpaired electrons. So if we were asked about the unpaired count here, we'd have 2 unpaired electrons. And so again, this would be the 4s2 and then the 3d2. Now, an important question or an important thought is, well, where are these electrons most probably centered around the nucleus of this atom? Well, if you picture the 22 plus nucleus of titanium, let me actually draw this down here with a little bit more room. So imagine that 22 plus nucleus of titanium. So the 22 protons, however many neutrons are in that nucleus. So if we picture the full configuration, this might be interesting to kind of think we'd have like the 1s with 2 electrons, we'd have the 2s with 2 electrons, we'd have the 2p orbitals, so these would be the 2p orbitals, we'd have the 2px, the 2py, we'd have the third one, which I'm not going to draw, but in 3 dimensions we'd have like a p orbital sticking straight out of the page for the third p orbital. We'd have all that and sort of then followed by the 3s subshell, then we'd have the 3p just following along the periodic table, we'd have the 3p subshell here, and so then we'd have the 4s here. So for potassium and calcium, their sort of question is, where do I put my next 2 electrons? Do we fill into the D subshell or the S subshell? Well, you can see they're in the S block, so they're going to fill into the S block according to the periodic table, what we know about configurations. But the reason why they probably do so is, if you think about where the S block is, it puts the electrons further away from the nucleus for potassium and calcium, but then titanium's going to say, well, what about all this space here that's not being used? Why don't I put electrons, let me use a different color, why don't I use these orbitals here, and that's where the D orbitals are. They're going to use the space that's left behind in between the P orbitals. So it's going to use that like leftover space. Now you can kind of think then, this tells us a lot about why there weren't 1p orbitals. So presumably there's no 1p orbitals because there's no space here for the p orbitals to occupy, but between the 2 and 3, there was space. So between n equals 1 and 2, no space for p orbitals. Between 2 and 3, there was space for p orbitals, but there's no room for d orbitals then. So if we think about these p orbitals here, they're probably these ones here for the 2p. These are probably orbitals that are using this space here, not leaving much space between for 2d orbitals. So why are there no 2d orbitals? Because the p orbitals are taking up all the space near them. Then as soon as we go up into n value, then we can fill into our 3d subshell. So our 3d subshell is filling into the n equals 3 space. It's actually, those electrons are actually closer to the nucleus than the 4s electrons, but it just becomes kind of a question of electrons repel each other. So we don't necessarily want to pack electrons into d subshells until we kind of have to, until there's enough charge to pull those electrons in. So the difference between potassium, calcium, and something like scandium and titanium getting into the transition metal series is we start getting into higher positive charge to pull those electrons into that space closer to the nucleus, but then that's closer to other electrons leading to repulsion. So I think there's like something interesting here with this question, just getting us into thinking that it's actually the 4s electrons that are actually on average further from the nucleus than the 3d electrons. So it doesn't necessarily go the order of distance from the nucleus by the order we supposedly fill the electrons into our configurations. The n equals 3 space is all closer to the nucleus than the n equals 4 space. So it's like the 3s are closer to the nucleus, then the 3p, then the 3d, then the 4s. So it's like within a given shell, s are closest to the nucleus, and its p electrons a little further away, d electrons a little bit on average further away, and then we would get into the n equals 4 space. So this would go like the n equals 1, like 1s closest to the nucleus, then 2s, then 2p, then 3s, then 3p, then 3d, then the entire 4 shell, n equals 4, so the 4s, 4p, 4d, 4f. So this then leads to, when we start finally filling into the F block, we're actually filling in then 2 shells closer to the nucleus than the outermost shell of those atoms. So kind of interesting in how atoms are choosing to use space. You can think of it as there has to be a high enough charge to start filling into the area in between those subshells. So if we want to fill into the area between like p orbitals, have to be relatively large. If we want to fill into the area in between like d orbitals, you got to get up to the n equals 4 to have those f orbitals. Okay, number 8, at most how many electrons in a multi-electron can occupy the 2p subshell? I think this is a pretty easy question. So the 2p subshell comprises of 3 orbitals. So you'd have the m sub l combination of -1, 0, plus 1 because the n is 2, the l is 1 for that subshell. So that's why we have this range here for 3 orbitals. 2 electrons into each orbital, so we get 2 electrons per orbital, so I can get 6 max electrons into that 2p subshell. If you're coming in, this is the Chapter 6 review, number 2 from daily quizzes. Just 2 more pages for this to go, a few more comments about midterm 3, and then we'll head into a couple topics out of Chapter 7. I think some Chapter 7 topics actually will help reinforce a few ideas from Chapter 6. Which of these orbitals below is not a d orbital? Well, this orbital here looks like a p orbital. This is actually the py orbital. I don't think we get too much into the designation of orbitals and naming them, but the py is on the y-axis, the px is on the x-axis, the pz is on the z-axis. But the p orbitals have one set of lobes. They have one plane of symmetry, and that plane goes right through the nucleus of the atom. So the p orbitals have one of those planes of symmetry. S orbitals, of course, have 0 planes of symmetry. S orbitals could have those radial distribution plots, so like an n equals 1 might look like this for the 1s, the 2s might look like this, so we might have these radial nodes, so the 2s would have 1 radial node, but the nodes that we're talking about on this page are a little bit different. They're nodes through the plane of the atom or through the center of the atom. They're the nodes that are determined by the L value. So when L is 1, we have 1 node, so this is just a p orbital. So A is the one that's not a d orbital, and the 2 sets of lobes, the 3 other choices are exactly how we would picture 4 of the 5 d orbitals looking like orbitals of that variety. And so each of those orbitals is showing that we have 2 planes of symmetry, and so these all share having the L value of 2, so those are all d orbitals. There's one d orbital that looks a little bit different. One of the d orbitals, it's on the z-axis, not a very big detail, but then it has that donut ring, so we get the plane of symmetry through the center of the atom between the ring. And so that would be the dz squared. Again, I don't think I'd expect you to know that name is dz squared in particular or anything about the axis nature. Like I don't think I'd expect you to be able to name which of these is the dxy, the dxz, but you could picture 2 sets of lobes with the donut ring, 1 donut ring with the lobes would give us a d orbital. And then the last page from this particular packet, unpaired electron count for number 10. We're comparing phosphorus, silicon, phosphorus, sulfur, chlorine is from left to right across the n equals 3 group of the periodic table. Let's start with silicon. So silicon would be a neon configuration followed by a 3s2, 3p2. And so it looks something like this. 2 unpaired electrons, So silicon would have 2 unpaired electrons. So these two here. If I get the phosphorus right next door to silicon, phosphorus goes to the 2p3 configuration. So then we have an extra electron. So phosphorus has 3 unpaired electrons. Sulfur is right next to phosphorus. So we pick up the p4 configuration, add an electron spin pair. So I'm just following Hund's rule, trying to maximize the spin and spin pairing when I run out of orbitals. And so I go back to only having 2 unpaired electrons for sulfur, and then chlorine is a 3s2, 3p5, so we add in a final electron for these 4 choices, so we have just 1 unpaired electron for a chlorine atom. So of these choices here, phosphorus has the most unpaired electrons. So unpaired electron counts are just a way that we see that you have the right electron diagram sketched in where you're applying Hund's rule, maximizing the spin, following the Pauli exclusion principle. We want to put spin up, spin down in each particular orbital. And then if we have a degenerate set, remember we call these orbitals degenerate when they're equal to 3p3 orbitals are all degenerate, equal in energy, so we spin pair, and then maximize the spin in the same direction using all 3 orbitals. And then when we get to the 4th, we have the spin pair. And the same thing happens with the transition metals. We just have 5d orbitals, so if we're going across, we're just spin pairing up to 5 and then spin pairing from there. So we do the same thing within the d set, just with 2 extra orbitals. Valence count is, the issue of valence count is the outermost shell, so that part's pretty easy, but then when we have a lower unfilled subshell, we're gonna count those too. So vanadium is an example of that lower unfilled subshell. So vanadium is 3 across the D block, so vanadium is right next to titanium, so it would be a 4s2, 3d3. So you're just looking at this configuration here. Now, the reason why I wanted to make sure to talk about vanadium is you might have said, well, does this do one of those goofy anomaly things? Does this go to the half-filled D subshell? Just think of the configurations we asked you to come up with should all be the expected configurations. Don't worry about thinking, is this one of those goofy anomalies where it has a different configuration? Just think, what configuration would you expect? You'd expect us to fill the S block first, then the D block. We only have 3 unpaired electrons if we're asking for the unpaired count. But in terms of the valence count, n equals 4 definitely is the outermost shell, and then these 3 are in an unfilled subshell, so we add those 3 too. So for vanadium, we have 5 valence electrons. So valence just means outermost. The most important electrons for bonding are the valence electrons. We make cations, we're gonna use those valence electrons. We'll have to figure out which ones, that's part of chapter 7 to figure out cation configurations. But we'd go with 5 valence electrons for vanadium. Now, if we get to, let's do nitrogen next. So nitrogen has a 2s2, 2p3 configuration. So it's just like phosphorus, but in the n equals 2 row. So we have 5 valence electrons here too, because the outermost shell is 2. So we count the 2s and the 2p electrons towards the outermost shell. So the shell is defined by n. So therefore, we have 5 valence electrons for nitrogen as well. So we have 5 valence electrons here. And then antimony is Sb, and it's in the same group as nitrogen. So antimony has to have 5 as well. Without even doing anything, I have to know all the elements in a group together share the valence count. So all the halogens have 7, all the oxygen group have 6, all the nitrogen group have 5. So I know antimony as well will have 5 valence electrons. Now, if we wanted to come up with a configuration for element Sb, for antimony, it would be a krypton configuration, followed by a 5s2. We're filling into the 4d with all 10, and then coming back to the 5p for 3. And I just like to make sure that we see now why 5p3 and not some other number is because we're just filling in accordingly. Like think how nitrogen's a 2s2, 2p3, phosphorus a 3s2, 3p3, arsenic would be a 4s2, 4p3, and then we're just following along for antimony. So if you're stuck on is it 5s2 or 4s2 or 6s2, just think about all the other elements in the periodic table and kind of just follow accordingly along with what the numbers have to be. And then the row above us are filling into the 3D, so now we're filling into the 4D. This 4D is filled in terms of valence count, so only these 5 apply as valence electrons. Consider argon in its ground state electron configuration. How many of its electrons have an m sub s of -0.5? So it's like saying for argon, if we go from scratch, we have a 1s2, 2s2, 2p6, 3s2, and then 3p6. So all the electrons are spin paired for argon. This question, I could not ask this question for something that had unpaired electrons, like nitrogen or vanadium or any of the examples above with unpaired electrons. I don't necessarily know the spin up ones are plus a half. They're just either the plus a half or the minus a half. In fact, you don't even define which quantum number they are absent of applying a magnetic field. So you actually need to apply a magnetic field, and then the notation is just that the plus a half aligned with the field, the minus a half aligned against the field. So I mean, absent a magnetic field, you don't even know the difference between the plus and minus a half. But I do know if an atom has all spin up and all spin down, has a 0 number of unpaired electrons, then we just have equal spin up and spin down. So argon has 18 electrons. So of course 9 are spin up and then 9 are spin down. So I know whichever one are up versus down, I know that the up ones are there's 9 of them, the down ones there's 9 as well. So there should be 9 electrons that have a m sub s of minus a half. Palladium has an anomalous configuration, we're told, in this problem, and that configuration we're told is krypton 4d10. Palladium, we would have expected, it's in the nickel group, we would have expected it to be a 5s2 4d8, is what we would have expected. But within this configuration we're told here, how many unpaired electrons do we have? Well, that's pretty straightforward. It's just we have 5 orbitals within the 4d set, and they're all spin paired. So we have 0 unpaired electrons. The valence count is something like palladium is a very weird question. We probably would never ask about the valence count of palladium, because if you think about palladium, it has a completely filled n equals 4 subshell, nothing in the n equals 5. It would appear to have either 18 valence electrons by roll or 0. It's just not a good question first. So some atoms will have such a weird answer for the valence count that we would never ask you. So if you're picturing this thing, what would we answer for the valence count? Because we haven't filled anything in the n equals 5, and we have a 4s2 and a 4p6 part of this configuration. That's part of the krypton configuration. So how do we count this up? So we would never ask you for the valence count of something like palladium. Lastly here, what's the condensed electron configuration for neodymium? Nd is in the F block. It's element number 60. And so we know there should be 60 electrons assigned. Xenon is the nearest preceding noble gas. That's 54 of those electrons. And then if you're not sure, where do we fill into next? We're in the 6th row, so that's going to be 6s2. So we go 6s2. That takes us through cesium and barium. And then we're filling into lanthanum, cerium, praseodymium, neodymium. So we're getting to a 4f4. And so why 4f? Well, that's the first F block. Why is it an F block? We're filling into the block that goes 14 across, all the way across to YB, and then LU is actually probably best thought of to be in the periodic table. So let's come back to a better periodic table. We'll show you that we go lanthanum 4 across the neodymium, and then this would end the F block, and then this one here goes back into filling the D block. And so some periodic tables would put LU, lutetium here. Some periodic tables like this one kind of wedge it out, so you can kind of try to see that we would be wedging the S block down, squeezing in the F block. If you recall, the periodic table that lists all the blocks together without removing one is a way to view the periodic table. You can picture that. So just picture wedging the F block in right here. Okay, a few last things to say about chapters 5 through 6. These are the constants and equations you get for the exam. There was one particular equation that we didn't talk about in any of the review problems. That's this one here. And we come back to this equation a fair bit, so I wanted to come back to a topic with this equation. It'll be something we think about here in chapter 7 and chapter 8 as well. This is like Coulomb's law is the physics equation for it. It just relates to the charge of two particles, and that the EEL is the energy of electrostatic attraction or repulsion, or the electrostatic energy. And so the electrostatic energy, of course, is negative when we have a plus minus or minus plus combination. So we want the particles to be opposite in charge, and we get an electrostatic attractive force. We get a negative energy associated with bringing those particles together. And then if we have positive, positive, negative, negative, then those particles, if brought together, would have a high energy associated with them. They'd have a positive electrostatic potential energy. And then there's some involvement of distance. So if you had plus, plus, minus, minus, you want those particles to be far away so that they don't repel each other. So you want those particles to be further away as opposed to closer together. Plus, minus, they want to be closer together as opposed to further away. There's one question that I thought that kind of looked at electrostatic potential energy from one of the daily quizzes that I pulled up here. And that's just question 1. This is quiz 23. But just the first question's all we'll look at, then we'll head into chapter 7. But which change below leads to a release of energy? So if we separate two cations from each other, so in order for us to bring two cations together, we have to have a high energy. We have to somehow supply energy to bring those particles together. Then if we have those particles introduced together, if we separate them, then we can release energy. So if we're thinking of the electrostatic potential energy, plus plus would be like way up here. So if those particles were introduced together, we can release energy by simply separating the particles. So separating two cations would be a way to release energy from a system. Now, you could think of it as a lot of energy would have had to have been absorbed by those two cations to introduce them together in the first place. So we're just releasing that energy that had to be put into that system to bring them together in the first place. Breaking a chemical bond requires the absorption of energy. So anytime you break a bond, like HH bond going to two H atoms, this is from that like bond association energy section at the very end of chapter 5. This is always endothermic. So delta H has to be greater than 0 for breaking all of our covalent bonds. So there's some energy of attraction that's holding covalent bonds together that has to be overcome to break the bond. So all of our bond energies are positive. Bringing anions together, that always requires the absorption of energy as well. So if we have a minus-minus combination at far separation, that's fine, but if we want to introduce them to be next to each other, leads to an increase in energy. So a minus-minus to bring two anions together would require the absorption of energy, not the emission of energy. And so only separating two cations in this example will lead to a release of energy. Okay, so the review was quick. Hopefully between the review on a lot of chapter 5 stuff on Friday, here's some review on chapter 6, the review from Dr. Chafin on Friday night. If you guys check that out, the video is up on the link in the announcement that I made last, I think, Thursday. Between the practice quizzes, between the practice exams, hopefully you guys have a lot of practice problems. Definitely make sure to take a look at practice exams. I think you guys probably generally in the crowd that do the practice exams, but get good at trying to do these problems on your own. So a lot of times we can make sense of problems. We can see somebody solve a problem, like, oh yeah, that makes sense, that's good, and make note of it. But make sure you get some good practice between now and tomorrow to reinforce and hopefully be ready to go come midterm 3. Okay, so the unfortunate nature of this class is we have to move on to the next topic of chapter 7, but the good news is that I think it's very reinforcing of the topics that we're talking about here in chapter 6. And so the idea of chapter 7, it gets into the nuclear properties. How does the nucleus, kind of change the properties of an atom? From chapter 6, I think when you write like a 1s2 versus a 2s, when you write hydrogen's a 1s1, helium's a 1s2, that doesn't seem like a big change. There shouldn't be a big difference of property for those two atoms, but there is. We know hydrogen exists as a diatomic molecule, helium exists as a monoatomic gas. If you then say, well, it can't be that different to go to a 2s1 on top of that, well, lithium's a metal. And then if you go across the n=2 shell, eventually we transition back to being non-metallic. So there's a big difference of property of atoms as you just make a slight change in electron configuration. So it's not the electron configuration necessarily changing the properties of the atom. Maybe it is. Like helium has that stable filled configuration, so that's good for helium. But there's the interplay of that along with the nuclear charge. So the nucleus of the atom is changing as you go from left to right. That's dictating a lot of the differences between the properties that atoms have that we'll see here in chapter 7. And as we continue in chapters 8 and 9, we're going to put it all together in terms of bonding properties, three-dimensional shapes, etc. So what we're going to look at here in chapter 7 is just the first 4 sections of the chapter. So we'll talk a little bit about the development of the periodic table, but mostly about the trends of nuclear charge, what we call effective nuclear charge. That's the charge that the valence electrons or the electrons within an atom actually experience from the nucleus of the atom. We'll talk about how atoms have a varying size from left to right, top to bottom of the periodic table. We'll talk about the how ion size compares to atomic size. And then we'll look at ionization energies, electron affinities, and we'll skip most of the remaining parts of the chapter. The periodic table, one of the interesting things is that it was being arranged in 1870 by Mendeleev. So this process by Mendeleev started in 1870 when the first periodic table was constructed. And if you look roughly at the time of Mendeleev, you're kind of talking about elements that don't include the pink, green, or these blue elements. So we don't know much about these heavy elements. We don't know much about the post-uranium elements yet. And we actually don't even yet have discovered most of like the noble gases, and then some other elements on the periodic table as well had not yet been discovered. So we probably had about 2/3 of the elements discovered at the time that we're filling into and arranging the periodic table. And then this is also well before we discovered subatomic particles. You know, this is a good 30 plus years before we discovered the electron, before we discover the proton, before we discover atomic number. And so to be able to put together sort of a periodic table kind of began with the idea of the average mass of elements. So like the mass per particles of elements was beginning to be known as early as the alchemists. They were the ones that were, you know, taking ores and seeing what they can break them down into and seeing, okay, we keep getting to something that looks like iron, something that this other ore gives us copper, we get zinc out of this other one. And they're starting to get some of the properties of the elements through just trying to break down things that occur naturally and trying to see, okay, we keep getting to these like, you know, particular products. We get some gases sometimes, we get some solids, we get different solids depending on the ore. So that was like how the original elements began to be discovered. Moseley, I don't know if that's a name you'll ever see on a test, but Moseley actually was able to bombard different types of elements with X-rays, and then saw an X-ray frequency that was emitted by atoms. And so like he was able to discover atomic number just through an X-ray experiment, kind of a weird experiment that paved the way for just showing and supporting what ended up being the idea of the number of protons within the nucleus of the atoms. And even well before that was a thought or something that was known, just that we were seeing that like you could get a pattern for like H to helium to lithium to beryllium by increasing atomic number from a signature X-ray given off by those elements. So the primary thing we want to really talk about is, well, why do we get this periodic nature? We know the periodic table kind of like resets itself with each row, and each row has a slightly different length, and it's varying as we go from top to bottom of the periodic table. So we just want to try to understand why that is. One of the main ways we'll see is through something we call the effective nuclear charge. And so the effective charge, we'll see many of the properties of the atoms kind of depend on the outer valence electrons and how attracted they are to the nucleus. So how much charge is left over for a valence electron? We're going to picture sodium here to kind of get into this topic. So we know sodium should have a 1s2, 2s2, 2p6 configuration followed by the 3s1. So these would be what we call the core electrons, and this is, of course, would be that one valence electron for sodium. And if you think of the average size of these subshells, you know, you're picturing the 1s close to the nucleus, the 2s, and then the 2p subshell electrons being then the next biggest. So if you're thinking of the relative order of these electrons and how close they are to the nucleus, so probably the 1s closest to the nucleus, then the 2s, then the 2p, and then finally the 3s. So the 3s is on average furthest from the nucleus of all the four subshells that are being used by the sodium atom. And that's going to dictate that that one valence electron, therefore, is not going to have very much charge that makes it through those other electrons that are in the way. So the other electrons, these are all, of course, negative particles within these subshells. And of course, you know, we have within each p orbital 2 electrons, within each s orbital 2 electrons. So we have a lot of negative particles that are absorbing that positive charge. We have an 11 plus charge for the, you know, the nuclear charge of sodium would be 11. The atomic number is 11. So we have 11 protons in the nucleus. Those electrons are all kind of experiencing that charge, but the charge that's experienced by the electrons, we call it the effective charge. The Z effective, the actual plus charge of that nucleus that these electrons can absorb and observe or be pulled into the nucleus by, of course, the 1s experiences that greatest charge. It sees almost the full nuclear charge of the atom, and then it's absorbing that charge so that the electrons that come after it don't see as high of a charge. So then the 2s and the 2p, then followed by the 3s electrons, are experiencing, on average, a lower effective charge from the nucleus. So then if we start thinking about what makes the alkali metals and hydrogen kind of similar, is that they all have that one valence electron. And so all those elements share having one valence electron, other than hydrogen, there's a shell of electrons that's absorbing some charge, so that kind of on average, what we're going to end up finding is that our effective charge from left to right is going to increase, and then reset back to low with the first member of the alkali group in the next row down. So electrons are both attracted to the nucleus, but they're also repelled by the electrons. So there's a repulsion of the negative electrons with each other, and then there's the attractive force by the positive charge that they can observe or experience from the nucleus. And then as we get further from the nucleus, the experience, that effective charge that those electrons are experiencing is just dropping. So as electrons are further away from the nucleus, they're just simply not able to see as high of an effective charge. Let's make sure to define something. Nuclear charge itself is the symbol Z. So when we see Z effective, nuclear charge usually takes the symbol Z. Z, the total nuclear charge, is just the number of protons in the nucleus. So the Z for sodium would be 11 plus. And then the Z effective is how much of that positive charge makes it out to the 3s valence electrons? Not as much. Let's get into the next slide here. The next slide kind of shows us a picture of these orbitals in terms of radial probability distribution diagram. And there's a caveat in this diagram that's a very important one, and that these are the radial distribution functions for one electron systems. So if we only had one electron in the atom, there's a weird thing that happens. The 2p subshell appears to be smaller, closer to the nucleus than the 2s. That's because we're not looking, these probability distributions become quite complicated if you start filling in more than one electron. As soon as we fill in more than one electron, then the 2p subshell grows larger than the 2s subshell. So, and then another thing not shown on this particular diagram is the 3s. So the 3s should pick up an extra radial node. We see the 2s with its one radial node. We see the 1s closest to the nucleus. Should probably have the 2s closer to the nucleus for a multi-electron atom, the 2p growing further away from the nucleus. Oh, saw something going on over there. And so then the 3s not shown here, we would just picture having a second node. So it might look something like this. So this would be the picture of the 3s. And I mentioned in chapter 6 that we pick up the two nodes for the 3s, that the only thing that really is useful about knowing about these weird nodes is that you actually pick up having some probability for that 3s subshell, still actually having some probability, not a very high probability, but there's still some probability that those electrons are still relatively close to the nucleus. And so that's going to give us one of our top to bottom trends and hopefully help us understand a trend a little bit later. Now, in terms of calculating the effective charge, there's a couple ways we can do this. It would be Z minus S, where S is just whatever the sort of shielding effect is by the by the core electrons. And so this is like a shielding factor. And then the highest the shielding factor S could ever be is just directly equal to the number of core electrons. And so one way to approximate Z effective is you just take the nuclear charge and you subtract the core. So if we go back to sodium as our example, we have 10 core electrons. So 10 core electrons. Our approximation for Z is it can be approximated by 11 protons in the nucleus minus 10 core electrons to be equal to plus 1. If you do this for magnesium, if you compare this for like a magnesium atom, magnesium would have a Z of 12, but still 10 core electrons. So magnesium would be plus 2. You do it for aluminum, plus 3. So our effective charge is going to increase left to right. And then whenever we get back to, say, potassium, so potassium would be the argon configuration. That's 18 core electrons followed by a 4s1. That's going to have a Z of 19 minus 1, or minus 18 core electrons for a plus 1. So do you see how the effective charge is the thing that's resetting itself? It's the charge that from left to right is going to increase and then reset back to low with each next row of the periodic table. Now, this is an approximation. This isn't a direct calculation, so we'll have to think about how does this break down, and then so we can then understand if there's a top to bottom trend for effective charge. That's what the next slide will look at. So let's take a look at this slide here. So this slide's looking at a lot of things. So we're comparing here core electrons. What they're doing is they're absorbing nuclear charge. So the core electrons are like taking the overall positive charge, dampening some of it out from the outer valence electrons, but the outer valence electrons still have that little bit of probability being relatively close to the nucleus. So let's take a look here. So this figure is showing us the red curve is a Z effective for the 1s shell. So Z effective is a complicated term. Z effective, sometimes we use it in a way to say, what's the Z effective of the outer valence electrons? That's probably the most used way that we refer to the effective charge. But you could say, well, what's the effective charge of the 1s subshell? What charge does the 1s subshell experience within our atoms? And the 1s subshell is going to experience nearly the full positive charge of the nucleus. So if you notice here, the red dots are showing us that lithium sees about a +3 charge, all the way to argon sees about a +18 charge, and there's a tiny smidge where it's not experiencing the total full charge. So there might be a little bit of shielding by those little bit of probabilities that all those other subshells have of being relatively close to the nucleus, but they don't add up to too much. So you don't get maybe argon's 1s full charge experiences 18, but it's like 17.5 or 17.6. So that's kind of showing you that the other subshells are fighting a little bit for that positive charge by those probabilities. By, even when you get up to like an n equals 4, like a 4s subshell, how you still have like this probability here. It's like those probabilities are starting to add up as you get further from the nucleus. So then when we think of our left to right trend, we can see the left to right trend two ways. Either from the assumption that we made, the green curve being that the shielding factor S is just equal to the core electrons. And so this just shows you go from +1 all the way across to +8 at neon, and then you reset back at sodium, and then you increase all the way to argon just from +1 to +8 and reset back at +1 with each next successive row of the periodic table. So that is the green curve. So that just shows you get an increase in effective charge from left to right that resets itself with each row of the periodic table. That's the idea of effective charge, because there we get periodicity. This is showing us why our elements have a periodic nature. We have a much lower charge on the left side, much higher charge on the right side. You can already kind of start to envision why our elements have different properties. Which element do you think is going to be easier to remove an electron from? The one that has the one electron that experiences a low charge, or the one with a bunch of electrons that experiences a super high charge? It's going to be really hard to pull an electron off a noble gas. It's going to take a lot of energy. So the ionization energy is going to be really high for the right side elements. It's going to be really low, relatively low for the left side elements. Okay? So we could pick up a lot of properties just by understanding our effective nuclear charge trend. The blue and the yellow curves are looking at the effective charge but calculated with some more precise means, but you get the same trend. And so the goal of seeing the blue and the yellow curves here, the blue curve is looking at the advanced computational method, so it's looking at theoretical models to calculate the effective charge. The yellow curve is looking at something called Slater's rules, which I won't get into. It's described within one of those like shaded box sections of the chapter. If you're interested in checking it out, feel free, but we won't talk about Slater's rules at all. But you can see that the blue and the yellow curves have the exact same trend as the green curve, that they increase from left to right. They just don't increase maybe as much as you would expect. And then when you reset each row, there's a little bit of like a shuffling. So one of the things you see in the blue and the yellow curves is that when we start from like lithium on across to neon, that's this group here, lithium on across to neon, kind of looks like the green, just not seeing as pronounced of an increase as you might have expected from left to right. And then when you reset back to sodium, notice that it's actually a little higher. Notice that sodium has a higher effective charge than lithium did. So that's actually showing us our top to bottom trend here. That as N increases, as we go from top to bottom, we get a slight increase in our effective nuclear charge. So Z effective increases slightly from top to bottom. So as you go from the top of a group of elements down the group, as you go from lithium to sodium to potassium, the effective charge is going up, not by much, by a little bit, but then it still resets and increases across the group of elements, across the row from left to right. Now, why does it increase? Why does the effective charge increase from top to bottom? So as N increases, the electron's probability of being close to the nucleus is actually increasing. It's because of all of these probabilities here. It's that even as you go to a N equals 6, if you go to something like cesium that has a high N value, that you have all those little probabilities of that electron still being relatively close to the nucleus. So it's all of the fact that as you grow further from the nucleus, there's still a probability and a growing probability that electron is actually relatively close to the nucleus. So even your large orbitals are still finding ways to pack those electrons relatively close to the nucleus. And so then that's allowing those electrons to experience a slightly greater than average charge as you go from top to bottom. So to kind of conclude here, Z effective increases left to right and then resets with each row. and then it continues to increase from left to right, and it gives us our main periodic trend. It gives us our main trend that it's low on the left side, high on the right side, and it resets with each row of being low and then going back to high. When it resets itself a little bit higher than it did the previous row above it. So we just have a slight increase from top to bottom. Now let's think of how this plays a role in size of atoms, but before we start thinking of the left to right trend for atoms, let's think in general about the difference between the size of an atom before it makes a bond versus after it makes a bond. And so the non-bonding radius, we often call that a van der Waals radius, is half of the shortest distance separating two nuclei when they collide together, but they don't form a bond together. It's hard to measure these radii for anything other than the noble gases. Noble gases don't make bonds with very many things very often. So you can bounce like two argon atoms off each other and kind of see, well, how close do they get in a non-reactive collision? You have a hard time doing this with like two O atoms. If you collide two O atoms, they stick together. But the key is, if you somehow can know or predict or estimate the non-bonding radius, then when you make a bond, you're going to find that the bonding radius is less than the non-bonding radius because the orbitals overlap. The atoms and their electron shells will overlap together. So the key is that our bonding radius is half the distance between the nuclei. So if you take the nuclei distance here, the bond length, and divide it by 2, you're going to get then, if it's a diatomic molecule, if it's the same atom, then you can just cut the bond length in half, and that's the radius of each of the atoms in what we call the bonding atomic radii. The bonding atomic radius is always going to be less than the non-bonding radius. So the non-bonding radius would be bigger, so this is showing you that the non-bonding radius is bigger. If we make the bond, it's going to shorten that distance between the two atoms. So what it kind of shows us is we can think of atoms as either the size the atom would be if it didn't make a bond, or we could think of the size of the atoms if they made bonds. Most of the elements in the periodic table make bonds, so it's going to make more sense to track what we call bonding atomic radii trends, the size of the atoms when they're making bonds. Now we also have another complicating effect in that could be single bonds, double bonds, and triple bonds. And then single bonds are longer, double or shorter, triple or even shorter. And that's something we're going to have a hard time predicting and understanding until we get through chapter 9. So we're going to pretty much just compare what we call single type bonds here in this chapter, not worry too much about predicting the type of bond. We'll see that later when we get into 3-dimension structure. But the idea here is if you could picture a bond length, the bond length is going to be shorter than the distance that those two atoms would have in terms of the non-bonding radius. And so I just want us to see the difference between non-bonding radius bigger, bonding radius smaller, because the atoms overlap together when they make bonds. And that's because of the electrons being attracted to each other's nuclei. We'll see that come up as a topic in chapter 9 later. Okay, so this table here then is like showing you the bonding atomic radius. So I just wanted to make sure we knew what bonding atomic radius is. And then it also is going to show us how the noble gases are a little bit of an anomaly because they really don't make bonds together. So their only radii that we track are actually their non-bonding radii. So the first thing to kind of pick up here is we actually get the non-bonding radius for the noble gases. And then we get for the other atoms their single type bond average radius for the bonding atomic radius from left to right. Okay, with all that, if you were just thinking of the size of atoms from left to right, you would probably think there should just be a decrease in size simply because of the increase in charge. Now, you may have been thinking, well, if you go from 1s to lithium to beryllium, so let's go lithium across. If we're thinking the 2s1 to the 2s2 to the 2s2, 2p1, you may have been thinking, well, maybe we'll actually grow in size because we have more electrons. Electrons repel. Maybe the size grows from left to right. But the trend that's changing is the effective charge is going to pull those electrons in to be closer to the nucleus. So because of our increased effective nuclear charge, because of from lithium on across the neon, we increase in the effective nuclear charge, the charge those negative particles are attracted to, the size is pulled in to be smaller. So our bonding atomic radius from left to right decreases, and that's due to the effective charge that's increasing with that trend. So we have the increasing charge pulling those negative particles in to be smaller, closer to the nucleus. And then if we think from top to bottom, then it kind of kicks in, as you would expect, more electrons bigger in size. So our trends, as we go top to bottom, we get the increase in size. And so then if you compare fluorine on across to neon, why is neon bigger than fluorine? Well, fluorine shows its single type bonding atomic radius. Neon doesn't make a bond, we're just seeing its non-bonding radius. If neon could somehow make a bond, like a single type bond like a normal atom, it would be shorter. So we would predict it to be shorter, it just doesn't make a bond, so we don't know what that bond length would be since it doesn't form bonds in that sense. You can actually make bonds out of krypton, so krypton apparently can be measured to be a little bit shorter than its nearest halogen neighbor. But anyways, you get a decrease in size from left to right due to the increase in effective charge, and we get an increase from top to bottom in size due to electron repulsion using larger orbitals on average. So as you go from lithium to sodium to potassium, we're packing more electrons in, so we're using larger orbital, size goes up. Let's go ahead and take our quiz here for today. Keyword is water. Okay, so a couple of slides from now, we'll get into cation configurations, because there is something with configurations of some cations that are tricky. For most of the main group elements, it's actually pretty straightforward. If we're thinking of lithium going to lithium plus, of course we're just going to lose that valence electron. We're just going to lose that 2s1 valence electron. So lithium plus configuration is just a 1s2. Beryllium with its normal electrons would be a 1s2, 2s2, so we're just going to lose the larger 2s2 subshell. So beryllium 2 plus will just also be the 1s2 configuration, that noble gas configuration of helium. Same thing with like sodium, the sodium plus. Of course, sodium plus is just the configuration of neon. We just lost that 3s1. Magnesium 2 plus, the same configuration. Aluminum plus as well. So aluminum 3 plus comes from aluminum neutral, which is a 3s2, 3p1. It's just then the configuration also of neon. If you think of the anion configurations, their configurations, we'll see configurations as a topic in a minute, but it just continues along. So anions just continue to fill into the same subshell we were filling into. So these are becoming the configurations of neon. So O2 minus, we take the 2 open electrons that we need to fill the subshell, we fill them with electrons for O2 minus, just 1 for F minus. These are the configurations or the whole reasons why those were the actual charges of those ions from thinking of those valence electrons in the first place, starting way back in chapter 2. So now think about the size of the atom as a result of losing the valence electron. So if you think of the cations, of course they're going to become smaller. So cations always become smaller than their neutral counterparts because they lost the negative particle. They lost that big N equals 3 subshell electron, so they're now down to the core in terms of their size. So definitely removing electrons from an atom results in a decrease in size. Even if you could have an unstable cation that's not a normal count, even the radius would go, the radius of beryllium would be greater than beryllium plus, greater than beryllium 2 plus. So like losing an electron leads to a decrease in size, whether it's just the first valence electron or if it's both the valence electrons in the case of beryllium. So if you lose an electron, you're losing electron repulsion, so the atom size will always grow smaller, even if we haven't totally lost the entire shell of electrons that we have to lose. Now, beryllium plus, probably you won't be able to form that as a stable ion as much as you will like beryllium 2 plus. But it just shows you remove 1 electron, you decrease the size. It'll be helpful for us to think about later. Same thing with adding an electron, but the opposite. If we add an electron, we're adding to the negative particle repulsions. So adding an electron results in increased electron repulsion. So if we're looking at oxygen atom, if we add an O to go to O minus, then O minus has to be bigger than oxygen, then O2 minus has to be even bigger. So if we absorb an electron into an atom, make an anion, we're going to increase its size. We're increasing its size due to added electron repulsion. So anions have increased electron repulsion, and cations, of course, have decreased electron repulsion. And so you can compare K to K plus. K plus is smaller. Rubidium to rubidium plus. Rubidium is smaller. You can compare I to I minus. I minus is bigger, added repulsions. Bromine to bromine minus. Bromine minus is bigger. So all of our anions are bigger than their neutral atoms, and all of our cations are smaller than their neutral atoms. Now, it's very interesting in size when the electron count's the same. So isoelectronic is just a fancy word for same electronic configuration. Iso is that prefix for same. So ions that have the same number of total electrons have the same electron configuration. So what we see here is O2 minus has 10 electrons, F minus has 10 electrons, sodium plus has 10 electrons, magnesium 2 plus has 10 electrons, and aluminum 3 plus also has 10 electrons. These all have the configuration of neon, meaning that all of these atoms are the configurations 1s2, 2s2, 2p6. So they have the exact same electronic structure, so hence isoelectronic. And so then when we're picturing these atoms, we're picturing whatever their nuclear charge is. So we have the nuclear charge of the atom that varies. So we could be comparing oxygen, which has only 8 plus, versus aluminum, which has 13 plus. So we have that positive charge in the nucleus. And so then we have the 1s2, the 2s2, and the 2p set of orbitals. So now imagine you're an electron in a 2p orbital. Are you going to be more drawn into an 8 plus charge or a 13 plus charge? Which one do you think will make you go closer to the nucleus? Of course, it's the 13 plus charge. So if you look at the 13 plus of aluminum and its size, the size of aluminum 3 plus is a lot smaller than oxygen. Oxygen's bigger, has the exact same electron configuration, has 10 electrons as well, doesn't have the positive charge that aluminum has, therefore it's larger. So oxygen will look maybe more like this, and then aluminum will just look like we have smaller orbitals. So aluminum plus might look like this with the 13 plus, 8 plus of oxygen bigger. So think of that positive charge pulling those electrons in due to the attractive force. This comes back to that Coulomb's law. This comes back to that kappa Q1, Q2 divided by D is the energy of electrostatic attraction. So if we have a higher Q and we have a minus plus here, we have the negative electron. Let's think of the effective charge is increasing. The electron charge is constant. If we're comparing the electron's charge, it's still whatever the charge of an electron is, 1.6 times 10 to the minus 19 coulombs. But then the nuclear charge, if it increases, gives us a greater electrostatic force of attraction. We can then think if we put those particles closer together, then they have a greater energy of attraction. If you think of the energy of attraction for the particles being closer together we make particles, then, so we reduce their distance of separation, then we increase the energy of attraction. So we increase the attractive force the closer we put that minus with a bigger positive charge. So we can kind of come back to that Coulomb's law equation that we were talking about from chapter 5. Now let's compare a few things. We can compare the size of sodium versus fluorine. How would we compare sodium versus fluorine in terms of their relative sizes? Well, one of the things that they have in common is lithium. Like sodium's in the column with lithium, and then lithium's in the column with fluorine. So if I'm comparing the size of sodium versus fluorine, at first I might think it's a tricky comparison to make. I don't know which one's bigger, which one's smaller. But what I do know is I know sodium is bigger than lithium, just from our top to bottom trend, right? So from top to bottom, sodium has to be bigger than lithium. And from our left to right trend, I know that lithium has to be bigger than fluorine, right? Because size decreases left to right. So I know fluorine is smaller than lithium. I know lithium is smaller than sodium. Do you see how that shows that sodium has to be bigger than fluorine? So based on these two trends here, I know for a fact that sodium has to be bigger than fluorine. Okay, so at first glance, maybe I had a tricky time making the comparison. I had to think of an atom they both have in common. Now, I could have also used chlorine, like sodium's bigger than chlorine. Chlorine is bigger than fluorine. So sodium has to be bigger than fluorine that way as well. So we could have used chlorine. Just think of two atoms in a different row. Make the comparison to either chlorine or lithium to make the size of those atoms apparent so you can make a trend. Now, what about sodium versus sodium plus? Well, we know sodium plus is smaller. So the radius or the size is sodium plus. We use atomic radius as our idea of size. When we say the size of the radius decreases left to right, we're saying the size of the atom decreases left to right. So just think that the radius of the atom is just what we mean by saying size. So the size of the radius of sodium plus should be smaller than sodium, because taking electrons away makes the radius of those ions smaller than their neutral counterparts. We know the radius of F minus is larger than the radius of F. So adding electrons increases the size. Now, this is the really interesting thing here is then when we come down to comparing sodium plus versus F minus, even though sodium is actually a lot bigger, if we flip back, the video screws up if I go backwards, but if you look on the slide before, sodium's a lot bigger than fluorine. It's like almost a factor of 2 bigger than fluorine. But if you put that extra electron on F, it grows bigger. If you take an electron away from sodium, it grows smaller. And sodium has 11 plus. Fluorine's only a 9 plus in terms of their nuclear charge from their protons in the nuclei, and they each have 10 electrons. So sodium plus, its radius is actually smaller than the radius of F minus. It's because of this isoelectronic series. So anytime we have an equal number of electrons, the same electron configuration, we compare the Z, we compare the nuclear charge. Sodium has a higher charge, therefore it's smaller than F minus, and we get a change of the trend. So sodium is bigger than fluorine, neutral, where each atom just has its 0 charge, but then you give sodium its common ion of plus, fluorine its common ion of minus, you flip the trend of their size. The ionization energy trend kind of follows along pretty closely with what you would expect. There is a little bit of a caveat though, but our ionization energy, as you go from left to right, now the left to right is just going from top to bottom of the table, that we get a general increase from left to right. The next slide will show it a little bit more on the periodic table in the actual direction of left to right. But the energy that's required to remove the first electron from an atom increases from left to right. But then if you wanted to remove a second electron, that's this here, that's removing a second electron from an atom, that goes up. So to take a second electron away from sodium would be to remove a core electron from sodium. That takes a tremendous amount of energy. And if you notice magnesium, it goes from I1 to I2 to I3. That's removing the 3s2, one of those, removing the 3s1 that's left behind. So we have 2 valence electrons for magnesium. It takes 700 or so kJs for the first, even more for the second. The second ionization energy is always greater than the first. The third's always greater than the second. Whenever we start removing a core electron, it's a lot greater. So we get a huge increase whenever we start removing a core electron from a particular atom. So for aluminum, we can lose 3 electrons before the 4th is one of its cores and has a huge increase. Let's think about why we have this increase. If we're comparing aluminum, let's compare the size of aluminum this way. So aluminum is bigger than aluminum plus, which is bigger than aluminum 2 plus, which is bigger than aluminum 3 plus, which is bigger than aluminum 4 plus. So as you remove an electron, you make the atom smaller. So as you make an atom smaller, what do you do to the electrons that are left over? They're closer to the nucleus. They're closer then to the same charged nucleus. Does it take more energy to remove that electron as a result? Yes, because it's kappa Q1, Q2 divided by D. You made D smaller, the energy of attraction is now higher, takes more energy. And then when you start comparing the size of aluminum, you're going to have a small decrease in size until you remove that last valence electron. Then it's a lot smaller because you now just have that core that's really close to the nucleus, takes a tremendous amount of more energy. So this all comes down to kappa Q1, Q2 divided by D. So put those electrons closer to the nucleus, the energy of electrostatic attraction, the magnitude of that attractive force goes up. So as this goes down, the energy of attraction goes up. It takes more energy to remove those electrons as they're closer towards the nucleus. So I1, I2, I3 always increases. If you look at all of our atoms, each successive electron requires more energy. Let me end with this. Like the I2 is just the energy to remove the second electron. So what we're looking at for like aluminum is aluminum to aluminum plus is I1. So that's the 578. Aluminum plus to aluminum 2 plus another electron, that's I2. So just the energy to remove that second electron is the I2. So it's not the total energy to remove both electrons, just the energy to remove just the second electron. The energy to remove the third even higher. Okay guys, we'll stop here. We'll get into more of the left to right trends. We'll come back to thinking about our ionization energy trends and link that into some other properties of our atoms and wrap up chapter 7 on Wednesday. Good luck on midterm 3.
So if it was